this is the second lecture for the week of November 1st, and what I want to look at now is we want to look at the use of linear predictive coding. Now, unlike the Kestrel coefficient techniques, I don't have personal hands-on experience with linear predictive coding. It's just a method that we never really used. So as we go through these notes, I continue to use information from the Wikipedia site as well as the online textbook and the textbook that I've selected for your class from Hill. So let's go back and look again at sort of what we're doing. So in speech science and phonetics, a formant is this broad spectral maximum that results from an acoustic resonance of the human vocal tract. So in other words, this is what's happening with everything except your vocal cords. In acoustics, a formant is usually defined as a broad peak or a local maximum in the spectrum. For harmonic sounds, this formant frequency is sometimes taken as that of the harmonic that is most augmented by a resonance. So the difference between these two definitions resides in whether formants characterize the production mechanisms of a sound or the sound itself. In practice, the frequency of a spectral peak differs slightly from the associated resonance peak unless you just happen to be lucky and the harmonics line up with the resonant frequency. So a room can be said to have formants characteristic of that particular room due to its resonance. In both speech and rooms, formants are these characteristic features of the resonance of the space, and they're said to be excited by acoustic sources such as the voice, and they shape or filter the source's sounds, but they're not the sources themselves. So here we see three different formants, the sound of I, U, and A, and you can see how the first two formants, the first two peaks vary differently. You have F1 and F2 here, you have F1 and F2 here. Here they're very close together to me. This one is a lot harder to distinguish that these are two instead of just one broadened peak, but you can kind of see that when you get down toward the end. So formants are basically distinctive frequency components of the acoustic signal that is produced by speech or song or musical instruments. The information humans require to distinguish between speech sounds can be represented purely quantitatively by specifying peaks in the frequency spectrum. So the formant with the lowest frequency is F1, the second is F2, the third is F3, and so on. The fundamental frequency or the pitch of the voice is sometimes referred to as F sub 0, but it is not considered a formant because in itself, while it provides energy to make the sound is actually made by the vocal tract. Most often, the first two formants, F1 and F2, are sufficient to identify the vowel, and the relationship between the perceived vowel quality and the first two formant frequencies can be appreciated by listening to these artificial vowels that are generated by passing a train of clicks that simulates the pulse train coming from the human vocal cords through a pair of bandpass filters that then simulate the vocal tract resonances. So front vowels will have a higher F2 and low vowels have a higher F1. Lip rounding tends to lower F1 and F2 in the back vowels and F2 and F3 in the front vowels. Nasal consonants usually have an additional formant at around 2500 hertz, and the L in liquid has an extra formant at 1500. The English R sound is often distinguished by a very low third formant, usually below 2000 hertz. So the summary then of these statements is that we can look at the formants of speech and pull out specific vowel sounds based on the characteristics of their frequencies. So here are some average formants for a male voice, F1 and F2, and you can see the vowel sound. Now, these symbols come from the International Phonetics Association, and so you can look that up on their website to know what exactly it is you're looking at. But the important thing here is the range that you can see. The lowest thing in the male voice that you're looking at is probably 235. The second one's occurring at about 2100 hertz, and you can see the associated differences. So in normal voice speech, this underlying vibration that the vocal cords produces resembles a sawtooth wave that's kind of got a lot of rich harmonics. And you have all taken a basic signal processing class, done a Fourier series, hopefully, of the sawtooth, and you know in the sawtooth that you get a pretty rich harmonic structure. So if the fundamental frequency of one of the overtones is higher than a resonance, then you only weakly excite the resonance, and the formant usually imparted by that resonance is mostly lost. So an example of that is when you have opera singers who can hit very high notes, opera sopranos, who can hit very high notes and sing at very high pitches, you often cannot distinguish the vowel sounds. So I don't know if any of you have ever, as a novice, listened to opera. It's one of the things that a lot of people don't care for about opera, is you do lose some of the understanding of what's being sung if you're not, kind of a trained listener. So control of resonances is so basically, if usually your fundamental frequencies are lower than the formants. If you get higher than the first formant of the vowel, then you can lose some perception of what the vowel is. Control of resonances is an essential component of this vocal technique known as overtone singing. So the performer sings a low fundamental tone and is able to create sharp resonances to select upper harmonics, giving the impression that several tones are being sung at once. You may have seen videos, especially if you come from a music background, of people who are doing overtone singing. It's fairly common in certain parts of the world, certain parts of Africa, Asia. It's interesting to hear Tibetan monks chant in overtones. So you can easily find stuff on YouTube where you can watch this. Just Google overtone singing or overtone chanting, and you'll see that. It's really interesting. So you can use a spectrogram to visualize formants. And in spectrograms, as you know, it can be hard to distinguish between the formants and the naturally occurring harmonics, particularly in singing. But you can usually hear the natural formants in a vowel shape through these atonal techniques that are called vocal fry. We won't really talk much about this. Whether they're seen as acoustic resonances of the vocal tract or as local maxima in the speech spectrum like bandpass filters, they're defined by their frequency and by their spectral width. So different methods exist to obtain this information. Formant frequencies in an acoustic definition can be estimated from the frequency spectrum of the sound using a spectrogram or a spectrum analyzer. But to estimate the acoustic resonances of the vocal tract, you can use linear predictive coding. An intermediate approach consists in extracting the spectral envelope by neutralizing the fundamental frequency and then only looking for the local maxima in the spectral envelope. So part of the reason that I asked you on this homework to sort of go through and see if it was possible to use the Kepstral coefficients or the Kepstrom to be able to filter out the fundamental frequency is that sometimes that is often done as a first step. The fundamental frequency is removed, and then you look for local max and min in the remaining information. So linear predictive coding is mostly used in audio signal processing and speech processing to represent the spectral envelope of a digital signal of speech in compressed form, and then using the information of a linear predictive model. So we are beginning to talk about now how to process the information so that we can have audio compression. It is the most widely used method in speech coding and speech synthesis. and it's a very excuse me, it's a very powerful technique. So the way it works, you start out with the assumption that you have a speech signal that's produced by a buzzer at the end of the tube, and that's your voice sound, with occasional added hissing and popping for voiceless sounds like certain parts of speech. And you'll find the speech literature uses a lot of terminology, plosives, sibilants. Because we're not a speech therapy class, we're not going through in detail what those are. Just suffice it to say that there are what are called voiceless sounds. The S is one of them. And they're sounds that are made without the vibration of the vocal cords. So the source filter model is a pretty good approximation of the reality of speech production. The space between the vocal cords produces a buzz characterized by its intensity and its pitch. And then the vocal tract, meaning the throat and the mouth, forms the tube, which is characterized by resonances. The resonances give rise to formants or enhanced frequency bands in the sound produced, and then hisses and pops are generated by the action of the tongue, lips, and throat during certain forms of speech. So what linear predictive coding does is it analyzes the signal by estimating the formants, removes their effect from the speech signal, and then estimates, let me get back to where I was. And then it estimates the intensity and frequency of the remaining buzz. When you remove the formants, this is called inverse filtering, and the remaining signal is called the residue. So the numbers that describe the intensity and the frequency of the buzz, the formants, and the residue signal can all be stored or transmitted somewhere else. What linear predictive coding does is it synthesizes the speech signal by reversing the process. Use the buzz parameters and the residue to create a source signal, and use the formants to create a filter, and then run the source through the filter, resulting in speech. So in other words, this is how you would do speech synthesis. Easier to do because basically you've retained all of the information, you just separated it out into its different parts. So easier to do than to try and do a reverse process on your Kepstrel coefficients. So because speech signals vary with time, you basically usually do this on short chunks of the speech signal called frames. You generally have 30 to 50 frames per second to give intelligible speech with good compression. It's the most widely used method in speech coding and speech synthesis. It's used for speech analysis and resynthesis, and it's also used as a form of voice compression. Began many years ago by phone companies, used in several standards for voice compression. It's used for secured wireless, where voice has to be digitized and encrypted, and then sent over a narrow voice channel. And so we've all heard of Navajo 1, which is one of the famous audio codes, and that's what happened there. So linear predictive coding synthesis can be used to construct vocoders, which is where musical instruments are used as an excitation signal to the time-varying filter estimated from the singer's speech. Pretty popular in electronic music. And here's an example of a person who produced a computer music piece. And I'll play that for you if I can get it to come up. Go back and refine that. One of these is a link and one of them is not. I think this one will do it. I think I actually ultimately went to that YouTube link, but we'll hold on for just a moment. we may not be going to get there here. So let me see. Here we go. Let me try this one because this is really kind of creepy, I think. So we'll see if we can't. We'll see if we can't pull this up. So in other words, what this guy did is he used an energetic sound and then added some the impact of some filtering. Let's see. May have to just let you look it up on your own. Here we go.
You know, a lot of people think that in order to conceal carry, you're going to need a tactical belt and a set of jeans.
We will skip the ads and play this guy. And this goes on forever. So basically, example of linear predictive coding as done by Paul Lansky using linear predictive coding in a vocoder. So kind of a interesting and mildly creepy, maybe appropriate for Halloween slide. So as you know, the human voice consists of these sounds that are generated from the vocal cords. This produces this periodic waveform. It's filtered by the nose and throat. Produces different kinds of harmonic content. We've talked about the fact that you have other sets of sounds known as unvoiced and plosive sounds. The vocoder looks at speech to determine how the spectral characteristics change over time, and the result is a series of signals that represent these frequencies at any particular time the user speaks. So the signal is split into a number of frequency bands, and then the level of the signal present at each band gives this instantaneous representation of the energy content. In the encoder, this input is passed through a multiband filter, and the output of each band is measured using an envelope follower. And the signals from the envelope follower are then transmitted to the decoder. So this is a big part of what allows a lot of compression to go on. The decoder applies them as control signals to corresponding amplifiers of output filter channels. So unfortunately, I don't think I have a figure of this. It would be really useful to have one. So basically, you have your input, and it's filtered, and then you sort of measure using an envelope follower. You measure the signals, you transmit those to a decoder, and then the decoder uses them to control the amplifier outputs. And so that's how you can get synthesis. Information about the instantaneous frequency of the original voice signal is discarded. It turns out this was not important for the original use for encryption. The fact that you discard the original voice signal is kind of this dehumanizing aspect that makes it useful in creating special voice effects in popular music and audio entertainment. So then instead of a point-by-point recreation of the waveform, the vocoder process sends only the parameters of the vocal model over the communication link. So that's what you're hearing when you listened to this short YouTube segment that I played. The human characteristics, the fundamental frequency, the human identifying features are gone, and so you're just listening to the spectral characteristics of the formants. So basically, when you do this, the bandwidth to transmit speech can be reduced. and that allows more speech channels to utilize a given communication channel. So, for example, a radio channel or a submarine cable. Analog vocoders typically analyze an incoming signal by splitting the signal into multiple tuned frequency bands, and then they reconstruct it by sending the carrier signal through a bunch of tuned bandpass filters. The typical robot voice, the carrier is noise or a sawtooth waveform. So this kind of robotic aspect of speech that you sometimes used to hear, especially in the early days, is once again lacking the specific human part of the voice and just excited with noise or a sawtooth. And these usually have between 8 and 20 bands, which is not inconsistent with the human ear's number of frequency bands that it processes naturally. So even with the need to record several frequencies and add unvoiced sounds, the compression rates of vocoder systems are impressive, typically capturing frequencies from 500 to 3400 hertz. Most of the frequencies had a sampling rate of about 8 kilohertz. The sampling resolution is typically 8 or more bits per sample resolution for a data range of 64 kilobits per second, but a good vocoder can give you a reasonably good simulation of the voice with less than that, about less than an order or more than an order of magnitude reduction in data. So significance for compression. That's the only application I'm really going to go over of linear predictive, or the applications of linear predictive coding. So you can see you can get interesting audio effects. You can get significant compression by order of magnitude or more. And you can also get information about the content of the formants. Now, what I did not find is I did not find the output of linear predictive coding algorithms to really be widely used in neural network or speech recognition systems. So that may be out there. I didn't do an extensive search. I did a minimal search. So whether or not they can be trained for either speech or speaker recognition, an unanswered question, or whether or not that's commonly done. I mean, you can use anything to train a system, but I don't think it's commonly done with linear predictive coding. I think it is mostly done to compress speech and audio, or, as you saw, to create some of these special effects. Okay, well, that concludes what I want to discuss on linear predictive coding, and concludes the materials sort of prior to any machine learning that we'll look at, with the possible exception of we may do a brief examination of the use of hidden Markov models.